I'm the next student of DPS. And first of all, I'd like to thank Kwanit and everyone for having me over here. And also would like to wish all of you best of luck for all of your future endeavors and whatever you want to do later, may it be in mathematics or any other stream. So basically, I shall be taking three talks on inequalities based on whatever has been already delivered to you by Kwanit, Sahil, Ahir, and them. So it's basically you already know something about order properties in R and Q, some other inequalities like AMGM and stuff. So I shall be developing on those, and I'll be introducing you to some more inequalities which are useful for the Olympiads or later on in entrance examinations like IIT or ISEC. So let us start over here. Actually, I'll try to share my screen over here. Kwanit, if you could just tell me whether it's actually getting shared as I start. Um, just a second.
Yes, I can see.
It's getting shared, right? So just a second over here. Let's call it inequalities. Really sorry over here. Okay. So we shall be looking into inequalities. So today's objective shall be these topics. First of all, as Kwanit has told me, I'll be assuming you know these stuffs. Uh, I'll That is, if we have a comma b greater than 0 real numbers, then a plus b by 2 is greater than equal to root over ab. This thing. I hope you have proved this using the square inequality, which comes from the order properties. For all x belonging to R, x square greater than equal to 0. With equality, I'll write this with equality. WEQ means with equality if and only if x equal to 0. If x not equal to 0, then x square is strictly greater than R. And finally, triangle inequality. So triangle inequality, which says in two variables, it's basically for all a comma b belonging to R, mod of mod a minus mod b is less than equal to mod a plus b is less than equal to mod a plus mod b. It's very easy. It's just proving this part would imply this part, and I'm sure you have seen the proof. Like that proof has been discussed. So now the first thing which I discussed today is how we can generalize our square inequality to some more variables, and then also how we can generalize AMG. So the very easy consequence of the square inequality be the following. For all x comma y comma, rather not x y, I hope you're familiar with finite sequences. Like when I index like this, what I mean, and to xn, I mean there are n real numbers over here. By this, I mean there are n real numbers, and they are called x1, x2, dot 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 xn. I'm sure you already know how what we mean by this notation. It's basically a finite sequence, or if you know functions, like it can be thought of as a function from this set 1 n to the real numbers. X can be thought of as a function with x of I equal to xi, which is a real number by definition. So I'm sure you know this part well. we have, if x1 to xn are real numbers, then x1 square plus x2 square plus dot plus xn square, this thing is greater than or equal to 0 with equality if and only if x1 equal to x2 equal to dot equal to xn equal to 0. Well, first of all, by using the sum properties and of order, we already know that xi square is greater than equal to 0 for all I belonging to one n, this set. This is obvious using the single variable square property and just the single variable square property, nothing else. With equality, if and only if xi equal to 0. Now you take a sum over here of all these xi squares, and the RHS are zeros. So 0 plus 0 n times is 0. So what it becomes is x1 square plus x2 square plus
Dada,
plus. Huh,
what did you
what?
write after that greater than equal to 0 in the first line? After that, w dot example.
Oh,
What
it's
did
a
you write?
w dot eq. I told in the last page, but in that w dot eq, it means with equality.
Oh.
Like this is the situation when equality will hold. And by if and only if I'm sure you know, it's the only, I mean that it's over here equality will hold, and this is the only situation in which equality holds. Like there is no other situation. Is it clear? Hello? Um, is it clear? Actually, I can't see the chat or any other screen.
Yes.
Yeah.
Okay.
Yeah.
Okay. Yeah. Okay then.
Yes.
This is with equality. Okay then. I'll continue over here. Uh, Now I take sum over here of x from x1 square greater than equal to 0 if I equal to 1, x2 square greater than equal to 0, I equal to 2 till n. So xn square greater than equal to 0. So x1 square plus x2 square plus dot plus xn square is greater than equal to 0, taking sum of inequalities. But when does equality hold? Like it's sometimes it's very important to analyze the cases when equality holds, because yeah, when if you have already done, I don't know, or when you will do quadratic equations and discriminants, or even in Olympiad inequalities, if you have seen the past papers, questions come like prove this inequality. In which cases does this become an equality or something like that? So there you need to be careful and find out the cases where the equality holds. So over here I've written that this over here is the only case when equality holds. So any idea on how we can prove this? If x1 equal to x2 dot equal to xn equal to 0, then the equality holds. But in no other case, I claim that the equality will hold. For one variable, it's easy. But what about n variables? Any ideas?
Add up the inequalities.
Yeah, you can prove this. Like I said, inequality will hold, it's obvious. But what about the equality?
Every square is greater than 1, so basically it necessarily means that if the sum of
Uh,
squares must be greater than equal.
how is every square greater than 1?
Sorry, greater than equal to 0.
Yeah. Okay. And next, so sum of square is greater than equal to 0. This part is obvious. Like this, from here to here, it's obvious. We are just taking the sum. But what about the equality case? That's my question. When does equality hold? I've said that this is the only case when equality holds. But can you prove it?
Can I try?
Yeah, surely.
Okay, so let us assume that x1 equals to x2 equals to xn equals to 0. That is the case we have proved. Suppose you have some other case where some variable is greater than or lesser than 0. So its
Okay.
sum is, so its square is going to be greater than 0 always. But for the equality to hold, we need the total sum to be equal to 0, and thus we must have something which is a negative of that square. But we all know that the square of a real number is greater than 0, and we cannot have negative numbers. So we get the case that there is no other possibility.
Yes, we can do that thing. What he said is, if we sort of what you said, I get that you're somewhat assuming an induction over there. That for n minus 1, the sum is greater than equal to 0. You already know it, and then you are using that fact over there, right? That if suppose xi is not equal to 0, then xi square is greater than 0. So that would imply for equality x1 square plus dot 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 plus xi minus 1 whole square plus xi plus 1 whole square dot plus dot 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 plus xn whole square is lesser than 0, because the sum is equal to 0. We are finding equality. And this is not possible because the sum of squares is greater than equal to 0, and that follows from this statement. And over here we have n minus 1 element, so you are somewhat using induction, and that's correct. We can do this. Very good. Well, you can also try doing something else which is pretty similar to this. Instead of straight away doing this inequality and summing it up, you know this thing, right? If a greater than equal to b, then a plus c greater than equal to b plus c. This is pretty obvious, I'm sure. So then again, can you prove that this quantity x1 square plus x2 square plus dot 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 plus xn square is greater than equal to xi square for all I belonging to our set 1 to n? Basically, you're adding this x1 square, this x1 square factor on, rather xi square factor on both sides, keeping all other things greater than equal to 0, which follows from our inequality which we just proved right now. So what you are saying, I'm just doing it directly. You were trying to find a contradiction over there, and I'm sure in proof writing methods you have seen one thing, that any proof can be given in 3 methods: direct, contrapositive, or contradiction. So what I'm saying is a direct proof over here. And if you have this thing, and we are assuming equality, so we have this. So 0 greater than equal to xi square, which in again, because of square inequality, is greater than equal to 0 for all I belonging to 1 comma n. That would be the implication of this statement. So that would imply xi equal to 0 for all I belonging to 1 comma, and that completes our proof. Okay, so why is this general square inequality important? We had a very good square inequality, and that seemed to be better in some extent, just one term. So why are we dealing with this one? So let's look at an example over here. And we got example 1. आगे पेज था, last page. Hello. Uh, do you have any problems? Should I go to the last page once? Would it be
No,
easier?
no.
Okay then. So let's look at one example over here. It would be a simple one over here. Wait a second. Okay. We need to prove this inequality and find the cases of equality.
What's the denominator?
Oh, okay. Sorry. Writing. It's 4 over there. And find the cases of equality. So how do you propose we should move forward?
Maybe we should
We
x plus y whole square y square plus 1.
your audio got a bit garbled over there. You just
I
repeat.
think we can do this. First, separate into x square plus 2xy plus y square. Um, then the next term is x square plus 2x square plus y square. Then the next
And
is y square plus half. Wait, plus 2 into half into y, half into y, and then add 1 by 4 to both sides, like
okay.
so on the left side. 1 by 4
So
to
if we
both
add a
sides.
1 by 4, we must subtract 1, and that's greater than equal to minus 1 by 4.
Yeah. And
So
then like so these
this
are
is if and
both
only if
x plus
x plus y
x
whole square, y
plus
plus
y
half whole
plus half greater than equal to 0 because cancelling out. Yeah, and this is only possible when y is equal to minus 1 by they can only be equal if y is equal to minus 1 by 2 and x is equal to minus 5. Yeah, yani ki
very
x is
good.
equal to even
Yeah.
only
So that's the idea over here. Yeah, exactly. And I think the first one of you also meant this one over here. So yes, this is the idea. But we can't just write like this. And your equality case is also right. The equality case over here would be x equal to half, y equal to minus half. But let's write it a bit properly. If we write it like this in the Olympiad, um, they would barely give you any marks because this doesn't make much sense over here. It's just some, what should I say, symbols and drawings, they'll say. So let's do it a bit properly. We have the idea now. Now we'll write it properly. The idea is perfect. If that's the idea we'll use. First of all, whenever we try to prove these inequalities, a good step is to go from the inequality to the final simple state. That is like over here we did x plus y whole square plus y plus half whole square is greater than equal to 0. But when we are writing it down in the final solution, we need to go opposite, in the opposite direction. Because we know the square inequality, we don't know this inequality, we need to prove it. So it's better if we go in the opposite direction. So what I mean by that, by square inequality, you guys write it in full forms. I'm just using um, some abbreviations over here. A square plus b square greater than equal to 0 for all a comma b belonging to R with equality if and only if a equal to b equal to 0. Set a equal to x plus y and b equal to y plus half over here. By closure, yeah,
What do we mean by set a equal to x plus 1?
we have a over here. A is a general variable. So we are just replacing a by x plus y and b by y plus half over here in this inequation. Then let's call this 1 maybe. From 1, x plus y whole square plus y plus half whole square is greater than equal to 0. And now you can do some calculation and shifting here and there, which we did earlier. This would imply first open the brackets, squares to get this thing plus y square plus y plus 1 by 4 is greater than equal to 0 with equality. This is important. If and only if x plus y equal to 0 and this is a, x plus y is at a over here, so a equal to 0 and b equal to 0. So what's a b? Y plus half. So y plus half equal to 0. Again, copy this step over here, which would imply x square plus 2xy plus 2y square plus y is greater than equal to minus 1 by 4. With equality if and only if x plus y equal to 0 and y plus half equal to 0. And this is equivalent to x equal to half, y equal to minus half. That's the only case of equality over here. So just write it down properly. So this is the process which you should use. Like you have some known inequalities and you go from there to the right hand side. Otherwise, sometimes some silly mistakes might occur. For example, a very common error in this Olympiad situation is, at least what I had seen, you are supposed to prove A greater than equal to B. You prove A greater than equal to C for some C. So proving A greater than equal to B, once you have proved this, should be sort of not equivalent, but easier if you can also show C greater than equal to B. But this might not be true. This part might not be true. But sometimes we make mistakes over here. And errors happen now and then, and it's very hard to detect these errors. And what we do, we first prove A greater than equal to C, B greater than equal to C, and then we somehow, by mistake or something, write A greater than equal to B. This is completely incorrect. You need to be very careful over here. This is a very common mistake, and sometimes it's hidden. Like over here, it's obvious. I'm just using A, B, and C as big terms. Over there, sometimes it's not that obvious, and you just miss it. So please be very careful. And the best way to avoid this part is to follow the opposite method. Do your rough work properly and then go in the opposite method. Then you'll realize that if you did make such a mistake, you'll realize where you made it. Because once you go opposite, you are starting with something which is right. And then if you are doing some hodgepodge or some mistake over there, it would become pretty clear and obvious. So whatever, these are some tips to write solutions and also to some methods which you should know, and also how you can deal with the equality case. So that's pretty much enough for this part. Now we come to an interesting thing, another generalization. This is the generalization of the AMGM inequality. Okay, before I generalize it to n variables or something like that, can you prove this thing? It's called the AMHM inequality of two variables. Or rather, I'll write it AMGMHM inequality. Inequality of two variables. It says again A comma B belongs to reals. Here another additional assumption would be not equal to 0. So basically, okay, I'll make a better assumption over here. Instead of sort of making two different statements, I'll just assume A comma B greater than 0. That would be better because I won't be using squares then. When A comma B greater than 0, then A plus B by 2 is greater than equal to 2 This is our AMGM standard thing. This is greater than equal to 2AB by A plus B. Or this thing is also written as 2 by 1 by A plus 1 by B. This is known as the AMGM-HN inequality for two variables. So let's try to prove it. I think that you already know how to prove it. This part, another thing, all these inequalities become equality in only one case, when A equal to B. This is the only equality case. So let's try to prove it. We'll show that both of these actually inequalities are equivalent to some extent. So the AMGM part you already know. A plus B by 2 greater than equal to root AB holds if and only if root A minus root B whole square greater than equal to 0, and this is true by the square inequality with equality if and only root A equal to root B, and since AB greater than 0 and no complex numbers pop out, this holds if and only if A equal to B. This is yeah, I just forget about it. Complex numbers, it's like you can't take root of negative numbers and have these liberties, like moving stuff and all. So what do you mean by the root of a negative number? That's a different story altogether.
Imaginary?
Don't. Yeah. Yes.
You mean by
Hello.
imaginary?
Yeah, imaginary numbers. So imaginary numbers with real numbers form a very huge set with very beautiful properties. That's known as complex numbers. Let's not deal with it right now. It's a bit too much at this stage. Let's just deal with simple inequalities with reals. I'm sure that the maths club team would provide you with some more details on complex numbers once they deal with polynomials and those stuff. But right now, let's focus on the inequality of reals. In complex inequalities make no sense and many things. So this is the case
I
of
have a
equality. This,
question.
yeah, surely.
In the first case, if we do transposition, we get 2 root AB by A plus B greater than equal to 2AB by A plus B. How is that possible? 2 root AB by A plus B greater than equal to 2AB by A plus B.
No, if you do a transposition and this invertendo over here, you have to also do it over here because you can't just multiply one inequality. So whatever
Oh,
you are
okay.
saying, it basically is the form which you are saying is basically 1 greater than equal to 2 root AB by A plus B is greater than equal to 4 AB by A plus B whole square.
Okay.
That's what you are saying. Yeah. And even the right hand side is pretty simple. Basically, you have this thing, you have AMGM. So just multiply by this thing on both sides. This is a positive quantity. This is greater than 0. Just multiply this on both sides. So the inequality is preserved. You can treat this as a constant. So what you get by multiplying is root AB, and this 2 by A plus B gets cancelled over here. So wait a second, let me write it down properly. That would be better. You are multiplying this to both sides of AMGM. So what do you have? A plus B by 2 times 2 root AB by A plus B is greater than equal to root AB times 2 root AB by A plus B. This is basically AMGM times a constant, positive constant. Again, equality will hold if and only if A equal to B, because this factor makes no effect over here. It's a positive constant. So it's equality whenever these two are equal, and that's A equal to B. But then do some simple calculation. This turns out to be root AB, and this turns out to be 2AB by A plus B. And which is equal to, again, what I said, 2 by 1 plus A by 2 by 1 plus B. So this is called the GM, and this is called the harmonic. So what we just saw is that AM of two elements is great.
And what are you proving?
Yeah,
So what are you proving again?
yeah. Surely we are proving this part. You already know this thing. Juan said that you already know this part. We are trying to prove this part. And if we know this and this, we have this chain. So is it okay?
Yes.
Yeah, and that's what we proved. By multiplying this factor to the AMGM, we proved that root AB is greater than equal to 2 by 1 by A plus 1 by B. And this is called the HM. And so what we have over here, this factor is again by AMGM and is less than equal to A plus B by 2. So this is called the AM, arithmetic mean. Arithmetic over here would mean some addition and adding stuff. So our average is basically the arithmetic mean. A mean means some kind of an average or a quantity which is between all these stuff. Sort of a, if you use geometric terms, centroid or a center of mass, one might say. So that's what is known as the arithmetic mean. This thing is known as the geometric mean. Instead of addition as the operation, if we use multiplication as the operation, over here to centralize it or to sort of bring it back to our range of consideration, we are dividing it by 2 to make it between A and B. So if we multiply A and B, how can we bring it back again between A and B? The best thing is to take a root to make the dimension same, or one might say, what should I say? Basically, this thing. If we assume, let me use something else. If we assume A less than B, then show that A is less than root AB is less than B. So that's why we take a root by after multiplication, because we might have that AB is greater than B. That's possible. So AB greater than A by this is, as it's again non-negative or rather positive over here. AB greater than B. That's possible. In fact, if A is greater than 1, this will happen because it's positive. So if we take a root over here, we are actually normalizing it back in between A and B. So that's why it's a mean. By mean is I was what I said. You know, in English also we use terms, English or in news or the stock channels you might have seen, exponentially increasing, geometrically increasing, and stuff. By geometry, we always mean some kind of multiplication over there by area and mensuration, all those stuff. And this thing is called the harmonic mean. This 2 by 1 by A plus 1 by B. The reason why it's called the harmonic mean is a bit, what should I say, not so obvious and non-trivial at this state. It's somewhat related to some physics and harmonic analysis and stuff. Once you go to senior classes, you'll see why this harmonic mean or sort of taking the reciprocal of the sum of reciprocals. That's what we are doing over here. It's basically 2 times the reciprocal of the sum of reciprocals. Why this is important, it will become a bit more obvious to you once you do some physics. I think you also already know resistance and stuff, a bit of it, at least the definition and things. And there is something known as parallel resistors and series resistors. You will see it in class 10 again, most probably, and again in 12. But over there, you'll see that parallel resistors have this as the equivalent resistance, or basically it's a mean over there again. These things might sound a bit weird and sort of out of the blue right now, but let's just say that we call this the harmonic mean. And we have AM greater than equal to GM greater than equal to H. That's what we know for 2 variables. Another thing would be important over here. As I said, all of these are means. So I just asked you to prove that the GM is a mean, or it's between A and B. So again, assume A less than B. Show that HM of A and B is again between A and B. You know interval notation? By this we mean HM lies between A and B. Show this thing. We can use tricks over here. Or show that this thing. A less than HM less than B. Try to prove this. Again, it's not hard. You can simply use properties of order and stuff. So for two variables, we have this beautiful thing called AMGM HM inequality. What about n variables? Okay, so for n variables, this can be generalized, but the proof is a bit lengthy. I won't say it's hard, it's a bit lengthy over there, the whole proof. So the generalized AMGM HM the statement is as follows: A1 AN are positive reals. M,
Numbers
yes,
A1 to AN are all positive real numbers.
positive real numbers greater than 0 reals. Okay. M equal to maximum of this set A1 AN, small m is equal to minimum of A1 to AN. These can be determined because both of these sets are finite over here. N is a natural number, so this is n many or finitely many of them are there. So you can find the maximum and the minimum. That's not a challenge. So our AMGM HM inequality would say capital M is greater than or equal to A1 plus A2 plus dot 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 plus AN by N. This is the arithmetic mean. Again, your known average, take sum and divide by the total number of values, is greater than or equal to nth root. I'm sure you remember nth root from your exponents. A1 times the product till AN. This is the product A1, A2 times AN. The geometric mean, which is greater than or equal to n by 1 by A1 plus dot 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 plus 1 by AN. The harmonic mean, which is greater than or equal to m, which is the minimum of these elements. And all these inequalities, if even one of these inequalities become an equality, all of these become equality, which is if and only if, with equality, if and only if m equal to m, or a1 equal to a2 equal to an. These two cases are the same. If maximum of these equal to minimum of these, that implies all of these are equal. And if all of these are equal, then the maximum and minimum are equal. So this is called the generalized AMGM HM inequality. So I think the first session would be over soon. Just go through this part once in your notes. And in the next session, I'll discuss some more problems using AMGM HM inequality and some more inequalities.
Dada, can you scroll the screen a
নিশ্চয়ই
bit?
উপরে যাবো তো আগের পেজটায়
No, down.
Okay, is it better now?
Yes, thank you.
Okay, AM is greater than equal to GM. To prove GM is greater than equal to HM. Okay.
Dada, some of them did it using induction.
Okay, so have you seen the proof of AMGM using induction for n variables? Have you seen the proof using induction of AMGM?
I have not showed them.
Okay, then that's wonderful. Actually, that's like a very good thing that you know the proof of AMGM. It's done using backward induction, the standard proof.
No, I
but
have not showed them. I have not showed them.
Oh, okay. No, even if you haven't showed them, like it's not required. You can assume AMGM HM, but if you know it, it's wonderful. And in fact, you can search it up on the net. how we prove AMGMHM. But I won't be discussing it as it's a bit time consuming and not that much important. If you want, we can send you notes. I can. Connect will send you a note. Okay, so let's look at an example over here using AMGM HM inequality. A simple one first. Okay, I won't select this. I'll go to next page and example 2. Again, we have a very similar situation. A1, AN are greater than 0 and reals, positive reals. It is known that A1, A2, AN is equal to 1. Show that 1 plus A1 1 plus AN is greater than equal to 2 power n. So how do you propose we go about this one?
Now, what have you written after 0?
Oh, acha, sorry. I've written reals. Basically, basically A1 to AN are positive reals. Are positive reals.
And second step is given.
Say this is given. Given A1, the product of all of them is equal to 1. So we need to show that the product of 1 plus A1 times till 1 plus AN, this is greater than equal to 2 power n. Also find equality cases. Also find equality cases. So how do you propose we go about this one? See, a very sort of confusing part, or rather misleading part over here. The left hand side is a product. So you might think that it's better if we do GM HM inequality, because over there we have a product greater than equal to basically a reciprocal of sum of reciprocals, or a sum that case. But should we go for GM HM inequality? What's your opinion?
Can I say?
Yeah.
First of all, we are having 1 plus A1. So by using AMGM in two variables, 1 plus A1 by 2 is greater than A1. Similarly, 1 plus AI by 2 is greater than root over of AI. So multiplying all the values, we get that 2 into root AI, like sigma of 2 into root AI. Then we get 2 to the power n is like the whole LHS is greater than 2 to the power n, and the root over of 1.
Yeah. More or less what you said is correct, but one thing, you need a small sort of group over there. It's not sigma over here, it's phi. It's a product.
Sorry.
This is not a sum, this is a product. So we have to be careful. It's 2 part n. But what you said is perfect. Basically, we need to do this. We can't do maybe there is a proof using GMHM, but it's preferably if you don't do GMHM, even though it's a product. Instead of that, we use order properties and AMGM over here. So A1 is greater than by 2 is greater than equal to root over A1. That's AMGM, because this is 1 times A1. So that implies 1 plus A1 is greater than equal to root over A1. So in general, we will have 1 plus AI
2 times
and times 2. Yeah, sorry. 2 times root over AI for all I belonging to 1 to n. So take a product, because this is again positive. So root AI is also positive. So this is greater than 0. We can take a product and still preserve the inequality. So taking product and using AI greater than 0 for all I. I won't be writing for all I belonging to 1 to n. You guys write it down. I'll just write for all I. That means for all I in the range which we are speaking. 1 plus a1 times dot 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 1 plus an is greater than equal to 2 per n, because all the 2's come together. There are n 2's. Root over a1. You basically have this thing. Root over a1 times root over a2. This again. This is failing me. Root over a2 dot 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 root over an. But because all of these are positive and we don't need to worry about it, root a root b equal to root ab. So this is not greater than equal to, rather it is equal to a1
root over 1
an.
because they
Yeah, which is equal to root over 1. This whole thing turns out to be 1. So this is 2n root over 1, given information, which is equal to 2 per n. So we have as desired. But what's the equality case? I won't be explicitly proving it, but guesses, or do you
The
have a
equality
solution?
case will be when a1 equals to a2 equals to dot dot equals to an equals to 1.
Exactly. So our equality case would be when all of these inequalities, this mini inequalities over here, become equality, and that's when this equality holds if ai equal to 1. So all of these must be 1, and that's the only case, or rather that's the case where equality holds, and that's in fact the only case. With equality, if and only if a1 equal to a2 equal to dot 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 equal to an is equal to 1. Okay, so this was a good example. Okay, so let's look at another example. Just let me check it once, whether it's the assignment.
Do you do this sum by taking the value a1 variables?
Actually, you're not that audible. Your sound is coming a bit garbled. Can you repeat, please?
I'm saying that can you do this sum by taking some value for the variables?
Never. If you are already you have been given a restriction, you can't assume some variable is some value and prove it. You should never do that. Even if you are assuming like that variable is some function of another variable, it should be a variable. You can't treat a variable as a constant. Never do that. That's something which you should never do. While doing inequalities or polynomials or equations, never assume values for variables, because that's not correct. Okay, so let's look at another example. This would be a bit different, because this time we won't have such a simple structure. Over here, we simply had to take EM, and the products were also given to us. Rather, the mini inequalities were also obvious over here. Which thing would give us that? So let's look at another example. Okay, first, maybe I'll go to the next page. That's better. Example 3. It's given A, B, C are greater than 0 reals.
Our screen is black.
The screen is black.
no, it's visible to me.
No, it's visible.
It's visible.
Yeah.
2.
Okay,
Visible.
so
I
let's
guess there is
continue.
some problem with her network.
Oh, okay then. Okay, so should we pause and do you need some time to figure it out, or should I continue?
She left the meeting. She was
Okay, then
having a
she's
network
trying
problem.
again. So it's okay. Let's continue in that case. I'll just state the problem. Okay, I'll just state the problem over here. It's given ABC are positive reals. Uh, in all our cases, if I don't mention, assume they are reals. Okay. So I'll avoid writing reals again and again. Just this is given, nothing else. Prove that A cube by BC plus B cube by CA plus C cube by AB is greater than equal to A plus B plus C. So ideas and find equality situations. That's always something which you should do, even if it's not given. It's 5 ideas, guys.
Can I say? Can I say?
Yeah, surely.
First of all, we can like use a generality like without loss of generality, A greater than equals to B greater than equals to C. In that case, like A square is greater than BC and A cube is greater than ABC. In that case, A cube by BC will be greater than equals to A, and similarly B cube by CA will be greater than equals to B, and C cube by AB is greater than equals to C. Hence proved.
So you mean to say if we have then C cube is greater than by AB is greater than equal to C. Just check. Is it right? What you said? It's the opposite inequality. This is what I was saying. You sometimes went basic. This is true, not the greater than equal to, which you said. And you're taking sum of two reverse inequalities. That's not something good. So okay, we can do it with B stuff. What you said, it's possible. I won't say it's impossible, but let's do it
If
with
this is
AMGM.
true, then how is the above one possible?
No, what he said, it's not true. Like what he said, it won't help us over here. So let's not use that.
Okay.
We can use this what he said, A greater than equal to B greater than equal to C, and do some inequalities. But over here, let's avoid that case. Let's do some simple AMGM. That's what we want to do. We are discussing AMGM, so let's stick to AMGM over here. And another thing important over here, like last time we had product comparing to a constant. Over here we have sum comparing to sum. So what when I'm saying AMGM, I mean AMGM HM. So it's up to you which one you should choose, AM or GM or HM. So I'm sorry, but I think your solution won't work over here. Let's try something else.
By
So any more
subtracting
ideas?
first term from so we'll subtract A from the first term, B from the second term, and C from the second term greater than equal to 0.
C from the third term, you mean, right? Hello? Hello.
Yes.
You meant
Yes.
C from the third term, right? That's the same problem. That's what he said. And that's not working.
Can this work somehow? I don't know if it will be working. A4 plus B4 plus C4 greater than equal to A plus B plus C into ABC. I don't
Yes,
know. Think
that's what's given. This Proving this is equivalent to proving a power 4 plus b power 4 plus c power 4 is greater than
Minus
equal to
ABC, but it's then coming if a to the 4 plus b to the 4 plus c to the minus ABC into a plus b plus c greater than equal to 0, which is easily proved.
How is it easily proved?
A to
That's
the
the
4
question.
plus b to the 4 plus c to the 4 will always be greater than 0 because they are all positive. And ABC, that product will always be greater than 0 because they are all positive. And a plus b plus c will also be greater than equal to 0.
So you just said that this is greater than 0 and this is greater than 0. Hence, this inequality is true. That's what I was discussing back then. A greater than equal to B, C, and B greater than equal to C does not imply A greater than equal to B.
I think
You
he
can't say
divided by the RHS and then instead of 1, he was
okay. So just think
Can I
about.
try once?
Yeah, surely.
Okay, so we first take the AMGM inequality for three variables, that A4 plus B4 plus C4 by 3 is greater than equal to ABC into cube root of ABC.
Okay.
Then we cross multiply to get A4 plus B4 plus C4 by 3ABC is greater than equal to cube root of ABC. Okay, now we
So you, by MGM,
use it
you have
for,
this thing.
yeah.
3ABC greater than equal to cube root of ABC. Yes.
Then we use it for ABC. So we get A plus B plus C by 3 is greater than equal to cube root of ABC.
Okay, and you also have A plus B plus C by 3 is greater than equal to cube root of ABC. So
Now we divide the two inequations.
okay, you are again saying that if A greater than equal to B and C greater than equal to B, then A by C is greater than equal to 1. So which is the same as showing that A greater than equal to C. So that's the same mistake again.
Oh, okay, sorry.
No, it's okay. This is a learning stage. We should avoid making such mistakes in the examination. Now we can make many mistakes. Okay then. Let me give you a hint. We'll prove this inequality because it's a bit tricky and beautiful in two ways. One thing I think you have seen in many proofs and also did it earlier, it's done using a claim or a lemma. That is, you prove something different, not exactly what's being asked to sort of we are being asked to prove, but something else, and then use it. So proof one. Let me call it proof one. We prove this lemma. We call it a lemma. For all x comma y comma z greater than 1, greater than 0, reals again.
Ma?
X square plus y square plus z square is greater than equal to xy plus yz plus zx.
we proved this in the last class.
Yeah, we
right?
proved this in the last
You
class.
can
Yeah,
continue.
proof. Just use
Is greater than equal to 0.
So what is a lemma?
this. Is a lemma is a like a mini theorem or a mini proposition, which is generally used in other situation. It's not something like a big theorem or a generally not a noteworthy result. Though we have some noteworthy lemmas,
Is
many of
PF
them.
proof?
Yeah, PF is proof.
Euclid.
Like Euclid's division lemma is over there.
You forgot z minus x to the power 2.
Oh yeah, over here there is a 2. Sorry. So basically you use this and the equality holds.
Equal to y equal to z.
Yeah, if and only if x equal to y equal to z. Now we use this over there. Using this lemma, a to the power 4 plus b to the power 4 plus c to the power 4 is equal to what? A square whole square plus b square whole square plus c square whole square. This is greater than equal to a square b square plus b square c square plus c square a square. Obvious? Just by the lemma. Here x is equal to a square, y equal to b square, and z equal to c square. But then again, what is this? AB whole square plus BC whole square plus CA whole square. And then again use the lemma. Use lemma again. And
How
you'll
does
get
how is it x is equal to y is equal to 2?
oh, it's not 2, sorry. My handwriting. It's Z.
Oh, sorry.
Yeah, no. Why are you apologizing? I should. And then again using the lemma, what do we have over here? AB times BC plus BC times CA plus CA times AB. Maybe I'll write it in the next line. CA times AB. Take ABC common from each term. See, you always have a ABC over here. ABC, another ABC. So this is equal to ABC times A plus B plus C. But that's what we were required to prove, right? That A power 4 plus B power 4 plus C power 4 is greater than or equal to ABC. So we have, with all this lemma and using it, we have A power 4 plus B power 4 plus C power 4 is greater than or equal to ABC times A plus B plus C. And that's divided by ABC. This would imply, by dividing by ABC, A square by BC plus B square by CA plus C square by AB is greater than or equal to A plus B plus C. And when does equality hold? That's an exercise for you. It's pretty obvious what should be the answer.
A equal to B equal to C.
Yeah, that's the only case. Just try to prove it. Very well. Now we basically did not use AMGM as such. We use the square inequality, that's it. So let's look at a proof using AMGM. This would be beautiful as well. So this is proof 2 of the same example. We sometimes, to make an inequality easier to prove or simpler to some extent, we introduce some ancillary or auxiliary terms over here. So that's some extra terms which get cancelled off or make the inequality better to some extent. So I need to you to tell me what I can introduce. I have the liberty to introduce it. Say a multiple of A. I say 3A. I want 3A over here. I want an 2 stuff over here so that I have this inequality. So what's the best thing I can get?
A is equal to B is equal to C. Is it?
No. I want 2 more terms which I can add over here so that I get this inequality. And it's a pretty obvious. I get a pretty obvious inequality over here. This inequality becomes pretty obvious. 2 easy terms. Okay, because this is your first such inequality, let me give you a hint. We have a B over here and a C over here. And over here, we don't have a denominator. So it's better if we can move this denominator.
Okay,
and
then
we know MGM.
PC then.
Exactly. A B over here and a C over here. And this is AMGM because A cube plus A cube by BC plus B plus C pi 3 is greater than or equal to cube root of A cube by BC times B times C, which is equal to A. And that's what we wanted. This is just part of one. And we can also do this with B cube by CA. So we would have B cube by CA plus C plus A is greater than or equal to 3B. And C cube by AB plus A plus B. Wait a second. I'm really sorry for that thing. Shortcut. Yeah, C cube by AB plus what is happening over here? Just a second. Okay, really sorry for the problem. C cube by AB plus A plus B is greater than or equal to 3C again. We have these three mini inequalities, as I said right now. Just add 1, 2, and 3 by
Then
preserving inequalities. We get A cube by BC plus B cube by AC plus C cube by AB plus 2 times A plus B plus C, because you can check that B, B, C, C, and A, which is a B over here, a B over here, C over here, C over here, and A over here, A over here. So it's 2 times A plus B plus C. This is greater than or equal to 3A plus 3B plus 3C, which is equal to 3 times A plus B plus C. So basically you can bring this over here, cancel it, and this would imply A cube by BC plus B cube by AC or CA plus C cube by AB is greater than or equal to A plus B plus C. That's it. That was our inequality. So including ancillary or extra terms is sometimes very helpful while solving inequalities. Well then. So before I go to more examples and problems, I'd like to discuss another important form or an important result of the AMGM inequality called the QMS AM inequality. Okay, scary terms.
What was the term?
Yeah, I'm just coming to that. This is called the QMS AM inequality. So what's the QMS? Quadratic mean squared. Very big term. Or we can call it QMAM. Let's call it quadratic mean over here. As many terms we can remove. So the quadratic mean is defined as the quantity second root of a1 square plus dot 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 an square by n. This is called the quadratic mean or QM an.
It's called squared because a1 square to
Yeah,
n.
exactly. That's what, but we can call it quadratic mean. It's cubic mean, quadratic mean. It's good. So quadratic mean inequality says QMN inequality. It's another inequality. The quadratic mean inequality says this quadratic mean is greater than or equal to the arithmetic mean. Again, equality holds if and only if a1 equal to with equality, a1 equal to an, 2 equal to dot dot equal to an. So another quick exercise, try it on later. Show that quadratic mean is indeed a mean. That is, it lies between the maximum and minimum of a1 to an. Not hard, but try it out. It's very important to verify whether what we are calling or whether the nomenclature which we did is indeed correct. So verify QM is a mean. Verify QM is a mean. Okay, so let's try at least to prove this one. So first of all, I'd like to ask you any ideas over here. How would you like to proceed with this one? Quadratic mean inequality. Let's prove it.
Question.
If we
Yeah,
can prove that a1 square plus a total an square is greater than a1 plus a total an whole square.
yeah, that's what we need to prove. Equivalently,
Something.
yeah, ask surely.
Uh, as QM is greater than or equal to AM, then it will also be greater than or equal to GM and HM.
Yeah, exactly. So we'll see that this whole chain would hold. This is greater than or equal to GM, which is again greater than or equal to HM. So again, this whole chain would hold. We are increasing the chain over here. We are adding a one more element to the chain, and this is sort of lesser than or equal to the maximum element of A1 to AN. So we are adding one more element to the chain. It's a very helpful inequality. So equivalently, as someone said, we'll try to prove phi n is greater than or equal to A1 plus dot 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 plus AN by n whole squared. Whole squared. Okay, so proof. Ideas?
Wait. So, we take the end to the right, like one of the ends from each side cancels out. Wait, actually, never mind.
Yeah, it's okay. Like you can share. It's not a problem. Yeah, we have to do those stuff, but okay. So let me help you out.
Yeah. So left hand side should become n into a1 square. So first we like cancel out one of the n's from each sides, and right hand side should become right hand side should become
Yeah,
a1 square plus a2 square all the way to an square plus 2 into in brackets a1 a2 plus a1 a3 all the way to an minus 1, basically all the possible combinations.
yeah,
After the left hand side would remain, and after that we cancel out one a1 a all the way to a n square from both sides. Left hand side
fair
would
enough.
become left hand side would become n minus 1 a1 square plus a2 square all the way to n square, and right hand side would become 2 into a1 a2 whatever, basically all the towards all the combinations.
Fair enough.
And then there should be an inequality in the form of if we multiply two on both sides, if like basically on both sides there should be there should be an inequality in the form of a1 minus a2 whole square plus a1 minus a3 whole square continuously to all combinations greater than 0. If that happens, then I think the equality can be proved.
Perfect. Yeah. So that's to some extent what we'll do. So basically, what he said is perfect. It's what should I say? It's exactly what we'll do. Just we'll go opposite. We first have this thing ai minus aj. Wait a second. Just write this thing. Great job. That's the solution. So use ai minus aj whole square is greater than or equal to 0 for all I comma j. Ai square plus aj square is greater than or equal to twice ai aj. Now we try to take a sum. We take a sum on all I not equal to j. So what happens in that sum? The left hand side becomes, how many times does each ai appear in the left hand side? We take a sum. Sorry. Take a sum over all 1 less than equal to I not equal to j less than equal to, or rather not, instead of not equal to j we can assume an order over here. 1 less than equal to I less than j less than equal to n. So how many times each ai appears in the left hand side?
n minus 1.
Exactly. So n minus 1 times. If you remove that ai, and for each other j not equal to I, it appears exactly once because we have a fixed order over here. So take sum. This would imply n minus 1 times the sum of ai's. So let me use this notation. This is called the sum notation. Sigma I equal to 1 to n. That is, we are running the sum from 1 to n. I think you already know this notation. This is greater than equal to the left hand side, no term is, so the right hand side, no term is repeated. So it is basically this thing. One less than equal to I less than j less than equal to n ai aj. Now we add a sigma ai square on both sides. So over here we would get n times sigma ai square is greater than equal to sigma ai square but if you know some if you this is a good exercise in induction, or you might have done it in your algebra courses. The right hand side over here is nothing but sigma ai I equal to 1 to n whole square. This is the right hand side. And divide both side by n square. We get sigma equal to 1 to n ai whole square by n is greater than equal to. Take the n square inside as n in each factor. Sigma equal to 1 to n ai by n.
Sorry, I couldn't follow from that. You change it to n into ai whole square.
This part is this implication clear?
After that line, I could not understand.
Okay, this line is clear, right? Okay, so this thing, the right hand side over here, sigma ai sum of all ai squares plus 2 times the sum of each different ai ages. This is nothing but sigma I equal to 1 to n ai whole square. This is the sort of, if you open the square and do something like a plus b whole square is equal to a square plus b square plus 2ab. Note that over here we have the square sum and 2 times the different things which appear inside the bracket, their product, and sum it. For a plus b plus c whole square, I am sure you have seen these. a square plus b square plus c square plus 2 times ab plus bc plus ca.
Okay, I got it.
And that's what we are doing over here. So what we just did over here is exactly this thing for n variables. Try to prove it using induction or any tool you know, or you can use another alternative method, some matching and stuff. But I won't prove this. This you can do it as an exercise, how this happens. Okay, then I'll just do this exercise, this part. Hence, we have the AM QMS inequality, a very useful inequality indeed. We'll see some more examples later of AM QMS inequality, but it's at present I don't have much examples there. Can have one simple example. Okay, let's not deal with examples right now for AM QMS. Now we want to generalize this. We just saw that the square root of the, or rather in the second form, this form over here, wait a second, this form, we have the mean of the squares is greater than equal to, the mean of the squares is greater than equal to the square of the means. This is the square of the mean or the square of the arithmetic mean, and this is the arithmetic mean of the squares. So we have the arithmetic mean of the squares is greater than equal to the square of the arithmetic mean. What about other powers? So we want to generalize this thing. We just what I was saying, that we just saw that mean, or rather I shouldn't write mean, just mean, AM of squares is greater than equal to square of AM. This is what we had. In fact, we have this triviality. AM of to the power 1, that is basically constants, is greater than equal to the power 1 of AM. This is a trivial statement, but it's still true. So what if I have some m greater than 1 or greater than equal to 1 rather? What can I say about am of mth power? M might not be an integer. M belongs to R. Am of mth power, what do we mean by rth power? Yeah, that's a question and it's hard to answer at this stage. Something related to exponent function and so on. But for rationals, you know what mth power means, right? Because you have seen, like, basically p by q, a power p by q is nothing but a power p whole power 1 by q, and so on. So what about this thing, mth power of am? We just saw it for squares and 1. So can we say, or rather guess, I shouldn't say can we say for certain, that over here we have am of mth power is greater than equal to mth power of am if m greater than equal to 1? Indeed, this is the case. With some analysis and stuff, and using functions and a bit advanced techniques, we have a stronger result than QMS AM or any other mean inequalities. So before that, I'd like to define some stuff before I get into the power mean inequality. Let A equal to a set. A is a set x1, xn, Rather, I won't call it a set. I'm not sure whether you're familiar with this name. It's a multi-set, or basically in set, all two elements are distinct. Like no two different elements of the same value can be there in a set. Basically, 1, 1 is the same thing as 1 as set, but this is a multi-set over here. So two values might be different. Sorry, I mean might be equal, or rather, to simplify, let's forget about multi-set. I'm sorry, might be a bit confusing. Let's consider this ordered collection, A equal to x1 to xn. It's an ordered collection of n real numbers. Let's call it n positive real numbers. It's basically a vector or an ordered pair, basically. Okay, then I'm really sorry. Yeah. This is a basically I think the notation is clear now. It's basically n positive real numbers in a certain order. The order is fixed, x1 to xn. We know the order. Like not the comparison order between them, but basically we know that they can be equal and stuff can happen like that. Just we know that they're n positive real numbers. Now, for all m belonging to R, define AM is equal to, this is tricky over here, sum of xi to the power m divided by n, I equal to 1 to n, whole to the power 1 by m, if m not equal to 0, and a0 is equal to simply the geometric mean, this product x1 to xn. This is a definition, a notation which we use. Now, I'll like to verify a few things. One. Yeah, surely. Yep.
Yes.
Surely. Yeah, I'll just go there. I'm really sorry for that.
I have noted it.
Okay. Yeah, okay. Everyone has noted it, so I'll just move on to the next page then. A1 is equal to AM of x1 to xn. A0 is by definition the GM. A minus 1 is equal to harmonic mean of x1 to xn. A2 is equal to our quadratic mean as we just did right now. Can you just verify these things? Next, I'd like you to verify, are you guys familiar with the concept of sequential limits or limits? It's too much to ask.
No,
But
not.
you're not familiar, right? Okay. So what I'd like you to verify is something which does not require limits. For all m belonging to reals, a let's call this This. Define x subscript capital M is equal to maximum of x1 xn x subscript small m as minimum of x1 to xn. Show that for all, maybe I won't use the small m notation over here. It's a function at the end of the day. Are belonging to our real numbers. X capital M is greater than or equal to AR is greater than equal to X small m. It's an X over here, sorry. X small m. So basically it lies between the minimum and maximum of our Xi's. So again, AR turns out to be a mean. So these two properties I'd like you to prove. The first one is some verifications and the second one is a property.
But AR is which mean?
AR can be any for real numbers. AR is defined as I defined above, right? So it's any mean which is defined in that form. Any number which is defined in that form turns out to be a mean. So if we define, it's a definition over here. AR is defined as the rth power mean of our collection A. I'm really sorry. Our collection A. So our collection A was basically this x1 comma xn, in which two elements can be equal and so on. It's basically an ordered pair. So there's no restriction on elements not being equal or anything. Just they need to be positive. That's important. So AR is defined as the rth power mean of A. This is the definition. Or we might say we define the rth power mean of A as AR because we have already defined AR as a function of x1 to xn and R. So we define the rth power mean. We call this AR as the rth power mean. So right now we saw that the arithmetic mean is the first power mean. The geometric mean is the 0th power mean. The quadratic mean is the second power mean, and so on. That's what I asked you to verify in the first property. But can you observe something? We already have this thing by the second property over here, this second property, as well as the first property, and our known inequalities about QM, HM, GM, and AM. We know that QM is less than equal to capital X M is greater than equal to QM is greater than equal to AM is greater than equal to GM is greater than equal to HM is greater than equal to capital X of small m. You already know it. In terms of our rather power means, we would write QM as A2, A1, A0, A minus 1. We can write this as XM or another celebrated notation, but it uses some concept of limit, so I won't prefer to write it. But if you want to know, we write this as A minus infinity. Makes no sense, right? Infinity function, infinity is not a real number. And this is called infinity. But actually it does make some sense. But we would stick to xm, x capital M and x small m instead. But if you want, you can write it as this.
So this involves all the numbers ever possible.
Yeah, R can be, or M can be, basically the argument over here can be all numbers ever possible between xm and x, and that's basically a claim, but that's pretty advanced. Instead, we'll do something simpler. We won't prove it, of course. As you can see, it's pretty. I'm sorry. You just go through this thing and note this, and then I'll move on to
How
the
can
next
it
one.
wait? How can it match the wait? How can it match the like the complete set of all the real number of all the real numbers between two numbers because this type of infinity that of all integers is a countable infinity while the other while the
Okay,
other
but
kind
yeah, you're right. But
is
where did I say that I'm only considering over integers? Right now, I'm doing integers 2, 1, 0, -1 are integers. But when I defined AR, I said it can be any real number. So over here we
okay.
have two uncountable infinities. So if you don't know about countability and uncountability, other people, it's okay. It's not important. But there's no problem with the cardinality over here. It's there. And in fact, when you're in class 11, most probably in some form you'll prove this thing. Okay, then I'll should I move to the next page, and I'll write the last different inequality for today, most probably, or maybe one more. Okay. So this is the final thing. We have defined the power means, and we just saw a property. Power mean inequality. Very special and very general inequality. The first general inequality which we'll see beyond natural numbers and so on.
Is it called the PM?
Yeah, you can call it the PM, or actually it's not required because it's a general term. Arithmetic, quadratic, geometric, those are specific power means. Like there are specific cases of the power mean, as we just saw. And power mean is a far, far more general term. But yeah, you can call this a PM inequality. It states, suppose x greater than y, x comma y real numbers, then ax greater than equal to ay with equality. If and only if our initial set x1 equal to x2 is equal to dot 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 xn. So let me just recall the notations. A is equal to x1 xn. AR is equal to 1 by r x1 to the power r plus dot 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 xn to the power r by n. If r not equal to 0 is equal to the GM, that is nth root of x1 xn r equal to 0. A far, far more general equality and pretty difficult to prove using simple tools, because it's basically, as someone said, you have uncountably many. Like, it's huge. It's not just infinity, it's a larger infinity than the normal infinity. Everything might sound as if it's senseless, but it's like makes no sense over here, meaningless, but ignore it. But it's a very beautiful inequality over here, and very elegant and very deep applications, and its proof itself, it's pretty advanced and pretty, what should I say, uh, has requires a lot of insight over there. But basically, this is the inequality statement. We have verified this inequality for 2, 1, 0, and -1. The QM, the this is the QM, this is the AM, this is the GM, this is the HM. But this is the general
Put
inequality.
r equal to 0, then the 1 by 0, it will become undefined in that case.
That's why I defined the function as r not equal to 0 and r equal to 0.
আচ্ছা, okay.
r not equal to 0 হলে এটা করব আমি, আর r equal to 0 হলে এটা করব। Okay then. This, as I just said, the proof itself is pretty deep, so there is no point discussing the proof or how to approach it. But it would be a great exercise if you read about this inequality and also try to prove it, not in its whole generality, if r is rational. This is something you can try. It's not that hard. Some basic tools would help you out. And first, just prove it for integers, and then the proof for rational follows. Okay then. Pretty deep inequality. Now, what have you observed something? Once you have noted this, I'll just move to the next page and just state one more inequality, and then stop for today. Just let me know if you have noted this page.
Yeah, I have noted.
Okay. Is there anyone who wants me to pause a bit? Because it's a bit deep and like you might be wondering why you're noting. So it's perfectly all right.
Did that equation come?
Which equation? This
That
one.
AR equal to X equal to the power. Yes, these two equations.
Basically, it's like generalizing what we did till now. If you observe, as I said, QMS is basically R equal to 2 case. That's how we define. And quadratic mean comes when you study ideal gases and stuff. Like when you study the gas and how the gas behaves if we neglect interaction and stuff, then the QMS comes. For the average, you already know average comes from statistics and stuff, basic statistics. The geometric mean, as I said, is generally something which is derived from geometry and studying means from products. The harmonic mean comes from electricity and chapters over there. So we got the means before and some special integer cases. Now we wanted to study for the real numbers. That's what we do. Generally, we start with integers or natural numbers and then we try to do for rationals and finally for reals. That's how it came. It's basically for some special cases of R, it came before. Yeah, it's a generalization or a grand theory, you might say. Okay, so
Dada, if R is equal to 0, then how is 1 by 0 possible in the power?
That's what I said. This is for R not equal to 0. The first definition is for R not equal to 0. And the second definition is for R equal to 0. Like you have seen functions defined as this, right? Fx equal to 1 by x, x not equal to 0, and 0, x equal to 0, and stuff. Basically, this is for this case.
Example of models like as a piecewise.
Yeah, it's basically a piecewise definition. We are defining for this part and defining for this part separately. Okay. So this is what's required for the A power mean inequality. Yeah, it has some general applications over there, and you might see some in the assignment. Very few of them, because uh, directly asking questions from power mean inequality is a bit dangerous, as
Rather,
I
if
said.
we go on increasing rather if we go on increasing will the value of the mean also go on increasing? Like if we put a equal
Exactly. So that's what we have,
r equal to 2.
because we have x greater than y implies x greater than equal to y. That's why if we keep on increasing, it turns out that till how much can it increase? We know that it's bounded above by the maximum value. So it reaches the maximum value. As we go to infinity and go on increasing r, it reaches the maximum value, or x capital M. And if we go on decreasing to minus infinity, it will
Till
keep on
minus infinity.
decreasing. But
It will
how
be
much
minimum.
will it decrease? Till x small m. That's why it's called a infinity and a minus infinity. That's the sense. But it requires, like, the formal stuff requires some limits, so let's forget using limits and stuff. Okay, then. This is a very good exercise to try to prove this for rationals. It's not that important, because you can assume for rationals, and for reals they hardly do ask it, the examination. Okay, so over here the generalization which we did is like taking the mth roots, or like we played with the powers over there, because we saw that three powers are appearing: the second power, the first power, and the minus one power, or the first negative power, the harmonic mean, that is. And we tried to play with it. So instead of playing with the powers, we can
What
also play with
exactly
the.
we had to prove again?
You need to
Like
prove this.
what?
You need to prove this power mean inequality. This exercise, right? You're referring to this exercise, right?
Yes. Yes.
You need to prove this power mean inequality for the case when x and y are rational numbers. This x and y over here, instead of x comma y belonging to reals, try to prove it. You can prove it if x and y are rational numbers. That proof is a bit easier. But you can forget about this proof. You can just assume this and sort of, I shouldn't say memorize, but uh, feel of how this is happening and assume it when you're doing stuff later on. Now, instead of you already know that AMGM inequality, right? This we have already discussed and you are already familiar with. We like to write it in a different form. Is this equivalent, or rather I should write n over here? These two are equivalent, right? Basically, we are splitting the denominator, the numerator, and writing it as 1 by n times a1 plus 1 by n times a2. And over here, we are using properties of the surd. So this is equivalent, right? This is also AMGM inequality.
Dada, wouldn't the bracket for the last one, the an into 1 by n, close after 1 by n?
Yeah, you can do that. Yeah, it's correct, because I was doing over here. We can do that. In actually, it won't matter whether you put the bracket outside or inside, because you're just applying that 1 by n to this bracket, right? So it doesn't matter that much. But yeah, because we are maintaining a pattern, we should maintain all the powers inside. This is equivalent, right? This is the AMGM inequality. But what's so special about these things? You can see that a1 and 1 by n are associated in some sense. Even over here, we have a1 and 1 by n. and so on. So now let's look at an example rather of AMGM's application. I'm sorry. This is so try to prove this. Easy stuff. Or rather just leave it till this.
Conclude from that one by n. Did you tell something after that? I got disconnected for a while.
Okay, no, I didn't say anything special over there. Just wrote this as like 1 by n and a1 are somewhat related. But what do I mean by related? Over here, it seems that everything has a 1 by n. So let's look at another example and we'll see what I mean by related. Can you prove this one? This isn't hard at all.
Can I try once?
Yeah, surely.
Okay, so we are taking two, sorry, not two, but three terms here, A1, A2, and A2.
Exactly.
So by AMGM inequality, we have A1 plus A2 plus A2 by 3 is greater than equal to
A2
root of A1 into A2 into A2. And so we can have the inequality.
That's it. Exactly. Perfect. Great. So this is the inequality. And this would imply a1 plus 2 a2 by 3 is greater than equal to cube root of a1 a2 square. Now let's write this example as we did above. So what do we have? This would imply 1 by 3 times a1 plus 2 by 3 times a2 is greater than equal to 1 by 3, rather not 1 by 3 over here, a1 to the power 1 by 3 times a2 to the power 2 by 3. So that's what this inequality would tell us, that the 1 by 3 times a1 plus 2 by 3 times a2 is greater than equal to a1 to the power 1 by 3 times a2 to the power 2 by 3. That's this inequality. This inequality is equivalent to this thing. So can we see some pattern over here? A very simple pattern that again 1 by 3 and a1 are related. 2 by 3 and a2 are related. So we can do this for n terms indeed. And you can do many exercises. Like for example, I won't prove this or discuss it, but again show this one. 2a1 plus a2 plus dot 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 plus an by n plus 1 is greater than equal to n plus 1th root of a1 square times an. a1 square a2. Just the square is only for a1 and rest all are single powers. And this can be also written as 2 by n plus 1 times a1 plus 1 by n plus 1 times a2 and so on. 1 by n plus 1 times an is greater than equal to a1 to the power 2 by n plus 1 an to the power 1 by n plus 1. Oh, sorry, 1 by n plus 1. This is the whole of it. So this thing can be generalized a bit. An exercise for you. First of all, if w1 dot 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 wn belong to R positive, that is R plus means positive reals.
Is it the
W1
weighted mean
plus,
equality?
yeah, we are coming to that one. W1 plus 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 Wn is equal to 1, then A1 W1 A1 plus dot 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 plus Wn A. Okay, sorry, I'll change the question a bit. I didn't intend this as an exercise. I intended this as an exercise. If W1 are positive rational numbers. Oh God, I don't know why this keeps on happening, but this basically W1 A1 plus dot 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 plus Wn An is a mean. First of all, by mean I mean it's between the maximum and the minimum, and so is A1 to the power W1, A2 to the power W2, and An to the power Wn. Now let's call this first thing as A and the second thing as G. Then A greater than equal to G. Assume AMGM inequality and try to prove this. Not hard at all. Very good exercise of what you have learned in AMGM. And just try to prove this. This is not minus G, by the way. We are calling this thing, this product is defined.
What was the Q plus set again?
Q plus is the set of positive rational numbers. Q is the set of rationals and Q plus is the set of positive rationals. And we also have that their sum is equal to 1.
So given these conditions, we have to prove that AM greater than A greater than G.
Yes. We need to prove A greater than equal to G, and also that A and G are both means. That A and G lie between the maximum and minimum of A1 and AN.
Where we will take them like A1 W1 times, then A2 W2 times till AN W1 times, and their mean W1 plus W2 greater than equal to then W1 whole root of A1 to the power W1, the AMGM inequality.
Yeah, to some extent we need to do that. Just be careful, W1 is a rational number, not an integer or a positive or a natural number. So there is a denominator term. So that's not something which comes in the AMGM. So you need to take care of the denominator as well. And also AMGM comes with a denominator. So just be careful and try to prove it. I won't discuss it over here. You guys try it on your own. I'll just generalize this and state it as a fact. This is called the weighted AMGM inequality. Or AMGM HM rather. And also you can define harmonic means as well. I'll just define the harmonic mean now. Wait a second. First of all, A1, AN, these are greater than 0. Or I should say, from now on, I'll write it as this, belongs to R plus, positive reals. W1, Wn also belongs to the positive reals, such that W1 plus W2 plus dot 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 plus Wn is equal to 1. Define A is equal to this is basically a sum, a weighted sum. These you might assume as weights or some values which are which you are assigning to these coordinates A1 and AN, and you're taking a sum over them. So it's again some arithmetic operation, and generally sum and arithmetic are treated to be equivalent. G is defined as we just did, A1 to the power W1, A2 to the power W2, and AN to the power WN. And finally, H. This is a bit tricky over here. H is defined to be 1 by W1 by A1 plus W2 by A2 and Wn by n. This is
plus between A1 to the power W1 and A2 to the power W2.
Geometric mean, it will be multiplication.
It's a geometric mean, so it's a multiplication. Geometric means multiplication.
Sorry.
Yeah. No need to apologize. So basically over here it's W1, the sum of W1 A1s. This is the product of A1 to the power W1s. And again, basically it's the sum of the reciprocals. So if you have two copies of A1, so it's A1, 1 by A1 plus 1 by A1. So it's 2 by A1. That's why this W1 comes atop A1. And that's why, and also this accounts for something else. So first, a thing which I always ask you to verify, AGH are means. Verify this. This is easy, not hard. And 2, this is the fact. A is greater than equal to G is greater than equal to H. This is a bit hard for the real case to prove this thing, but you can assume this. This thing that A is greater than equal to G is greater than equal to H is known as the weighted AMGM HM inequality. Sorry, the weighted AMGM HM inequality. Well, for the rationals, it's quite motivated why this comes. For the reals, you should assume that okay, rationals lead to reals and stuff. Like between any two real numbers, there is a rational number, and all those stuff. To get a bit motivated, but basically this thing holds. And when does equality hold? With equality, guesses?
When W1 equal to W2 equal to Wn and A1 equal to A2 equal till An.
Okay, the funny thing is you don't need W1 equal to W2 equal to Wn. That's not required. With equality, if and only if A1 equal to A2 equal to N. The W1 thing is not required for the equality. W1s can be anything, just they need to be positive reals adding up to 1. That's what's required. Rest, everything, they can be anything.
Yeah, when we will take the common, the sum will become 1. Yeah.
Yeah, exactly. Everywhere, when you consider these to be equal, they become a sum, and that sum is 1. So, no matter. Whatever you...
Dada.
What? What?
I got disconnected and I could not join.
Okay, so you want me to restate this part?
No, I actually missed from try to prove that if R is rational, that part.
Okay, that's quite a bit actually. Kwani, তুই রেকর্ডিং করেছিস?
না।
আচ্ছা। Let's do something. I'll send you the notes, whatever I've written over here.
Okay.
And I'm sure that most of you R means you are speaking about that power mean, right? AR.
Yes, which you said was important or not important. You grouped 1 by n A1 plus 1 by n A2, which is greater than.
Do you mean this part?
Please go a bit down.
A bit down, or up?
Sorry, up.
Yeah.
More. Yes, there.
Okay, this is a bit time consuming. You just go through these examples once, and maybe we can discuss later on, or Kwanit and I'll think of a sheet or something, and the Maths Club members will send you a sheet, and you can discuss with your friends or clear your doubts later on, because it will take some time, and I've written most of it over here. So basically, it's you see in this example, it would be clearer. Try to go through this example once and see how the power and the sort of coefficient of A1 and the power on the RHS are related. That's what I want to sort of extend and generalize. And once we do it, we get more stuff. So I'll request you go through it later, okay? So because we also have some restricted time, I'm really sorry about that. But if you have doubts, feel free to contact me on the next day when we have a session. We can talk about it, or even any Maths Club member or any of your friends over here. I am sure they'll be happy to help you. So should I move on?
Dada, 1 second here. I missed that part. A to the power A1 to the power 2 by n plus 1 till.
Oh, this product, right?
Yeah.
I should write it. It's this product is basically A1 to the power 2 by n plus 1 times till A to the power 1 by n plus 1. I should write that as well. 1 by n plus 1 and dot 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 an to the power 1 by n plus 1. It's basically the coefficients over here. Whatever coefficient appears over here is the power over here.
Okay, Dada, thank you.
Okay. So this is called the weighted AMGM, and W1 to Wn are called the weights, or some what should I say? You already know, like if you have seen your summative formative assessment system, or even the ISI stuff, entrance stuff, there are weights assigned to papers. Different papers have different weightage, right? That's what we say in grading. Even in numbers have some weight, and these W1 to Wn are the weights. And what we did over here as AM, GM, and HM, these are called the weighted AM. This is called the weighted GM, and this is called the weighted HM. I request you to go through all this once again, like whatever we did. It's like how we motivated this stuff, and maybe you can try once you know what this H thing, harmonic mean, what it is. Maybe you can try to prove this as well. Even in this case, define H for the rational case and prove that A greater than equal to G greater than equal to H. Okay then. That's quite some content which we discussed today, and I'm sure that you're feeling a bit overburdened and overloaded. But just to show the importance of this part, I would want to share one example. We have some time and some more energy left.
Meeting will end in 1 minute. So
Okay, then let's
because we have to
postpone it to tomorrow. Sorry, not
Wednesday.
tomorrow. When is the class? Wednesday.
Wednesday.
So let's discuss it on Wednesday.
Okay.
The first thing which we'll do on Wednesday is discuss this example.
Okay, thank you very much, Dada.
Ekdom. Thank you very much. And go through the assignment.
Thank you, Bhaiya.
Okay, thank you. Welcome. You're welcome. Chalo. Have a great day.